In this lecture, we discuss exosystems, systems of planets that orbit stars other than our Sun. Exosystems will help us answer many questions about the universe. Is our solar system typical? How do systems form? Are there habitable planets outside our system?
Humans have thought there must be exoplanets, planets around other stars, for a very long time. So we'll start by discussing their hopes and expectations. Then we'll explore the most important methods of detecting and studying exoplanets. Finally, we'll look at exoplanet discoveries, including the spectacular recent results of the Kepler Space Telescope.
The idea of exosystems is an old one. Just a few decades after Copernicus declared Earth a planet that orbits our Sun, astronomers began to think of other stars as suns. The Italian astronomer Giordano Bruno speculated that other stars were the centers of their own planetary systems, inhabited by beings much like us. The idea of life on planets elsewhere in the galaxy has been popular ever since. For centuries, it could hardly be called scientific because we were so far from having the technology to test it, but it made fine science fiction.
However, just within the last couple of decades, astronomers have discovered thousands of exoplanets. This gorgeous picture by Lynette Cook is an artist's conception, but the worlds we've discovered are very real. In the center is the Kepler Space Telescope, the mission that has discovered more of these worlds than any other. To us, the discovery of these new worlds is the most exciting development in astronomy. We're not the only ones who think so. Chris Impey says the recent explosion in the number of extrasolar planets, or exoplanets, is perhaps the most exciting phenomenon in all of science. Now, Impey is also an astronomer, so possibly we share the same bias. But by the end of this lecture, we hope to persuade you too.
Now that we have observed exosystems, we have lots of questions. What are these new exosystems like? How common are they? Are exoplanets in these systems like our planets? Do the big trends we see in our solar system apply to other systems, or is our solar system unusual in this? These are a few of the most important questions we'd like to answer about exosystems. Not only will answering them give us a clue to the likelihood of those intriguing aliens, it will help us better understand our own solar system.
What would you like to know about exoplanets? In your group, write down 1 or 2 additional questions that most interest you. Save a copy of your responses. You'll need them later.
How do we find out about exosystems? Can we actually see or photograph exoplanets? Mostly, we cannot. Planets are dim, and the stars they orbit are very bright. They're also very far away, so photographing an exoplanet is like photographing the light from a firefly buzzing around a searchlight on the other side of a continent. Only about a dozen exoplanets have been directly photographed as of early 2014, and even some of them are controversial. The first exosystem photographed is this one. 4 planets orbiting the star HR 8799. The trick is that light from the central star had to be blocked to detect the planets at all, so the odd blobs you see at the center are not the star, but rather residual unblocked light. Moreover, the image was taken in the infrared, wavelengths at which these hot young planets are at their brightest. They have been imaged repeatedly, so the arrows indicate their orbits. We've seen a few of these planets in visible light as well. Here's an example, Beta Pictoris b. Again, technology was used to block the light from the star, shown as a symbol, so that the planet could be seen. The planet is only a little brighter than the random background clutter in the picture, but other images taken in the infrared confirm that it's really there. Since it's so difficult to photograph exoplanets, we need a better strategy. the bright signal, the thing that's easy to detect from a distance, is the starlight, not the planet's light. So we need to look for the ways a planet modifies the starlight. If we see those traces in the light of a star, they will signal the presence of a planet even if we can't see the planet directly. While there are several techniques that have been used, the two most important ones are radial velocity and transits. Let's look at each of these.
Remember Newton's third law of motion? For every force, there's an equal and opposite reaction force. Now think about a planet in orbit. It goes in a curved path because it's feeling the force of gravity from the star. So the star must be feeling an equal force from the planet. Since stars are much bigger than planets, they don't move much. In the picture, the motion of the host star is exaggerated. However, in some cases, we can detect that motion, so it lets us tell that the planet is there. This is especially true if we view the system from the side, like this. Then we can see an effect known as the Doppler shift. As the host star approaches us, its light becomes slightly bluer or shorter wavelength. As it moves away, it becomes slightly redder or longer wavelength. A related example of the Doppler effect can be heard in the wavelengths of the sound a car makes as it drives past you. Stand by a road, listen closely. You can hear the shift from a high-pitched to a lower-pitched tone as the car approaches, passes, and recedes from you. Doppler shift is the basis of the radial velocity method. Note that to have a believable detection of a planet, you need to observe it over a few orbits, not just one. This lets you get a good estimate of how much force the planet is exerting on the star and rule out other possible causes for the Doppler shift. By 1989, radial velocity of exoplanet host stars was detectable, though barely so. The first possible detection of an exoplanet using this technique happened in 1989, when a group from Harvard discovered an object at least 11 times the mass of Jupiter, around the star HD 114762. This is on the boundary between a supergiant planet and the smallest class of stars called brown dwarfs, so it still hasn't been confirmed as a planet. However, in 1995, an unambiguous planet was discovered around the star 51 Pegasi. For more than a decade after this, radial velocity was the most important way exoplanets were discovered. The next way to detect a planet involves blocking the light. If the planet passes right in front of the star, we can see the star get dimmer. We call this a transit event. The effect is tiny. About 1% of a sun-like star's light would be cut off by a giant planet like Jupiter, and only 1/100th of 1% for a planet like Earth. It also only works for planets that are lined up just right so that they pass in front of the star as seen from Earth. For Earth-like planets orbiting at Earth-like distances around sun-like stars, only about 0.5% will be correctly aligned so that we can see a transit. This means that if we see one such planet, it's likely that there are 200 other stars with similar planets that we're not seeing because they don't line up this way. As with radial velocity, we have to observe transits for multiple planet orbits to be sure this is the cause. If astronomers observe in a succession of 3 matching transits with the same length, period, and depth, then the same planet has made just over 2 complete orbits, passing 3 times in front of its star. A planet in an Earth-like orbit around a Sun-like star would have to be observed for just over 2 years. When 3 transits have been observed, an object can be declared a planet candidate. But some form of additional evidence is needed to confirm or validate an object as a known planet. For example, radial velocity measurements from other instruments could be a confirmation. Real transit data looks like this. Notice the numbers on the vertical axis. The effect is subtle, only a few parts in 10,000. But nonetheless, it is clearly observable. We've looked at a few of the selection effects that matter for finding exoplanets, so now let's put all of them together. For all methods of observing exoplanets, there's a bias towards larger sizes. It's always easier to find large planets than small ones, so all surveys will have an overabundance of large planets. Both of the indirect methods of detection, looking for stars wobbling and looking for transits, will favor planets that are very close to their stars. Close planets move much faster than more distant planets, so we can see the effect of them pulling on their stars more easily. And close planets are more likely to line up with their star so that we see them transit. Also, all indirect methods of observing planets rely on observing one or more orbits, so planets with shorter orbits will be detected more quickly. On the other hand, direct detection techniques are more likely to find planets very far from their stars, since they're less likely to be lost in the glare of those stars. Finally, direct observation also favors very young planets. That's because these are usually observed in the infrared, so what we're seeing is the planet's own thermal radiation. Planets, especially large planets, form hot, so very young planets glow in the infrared much more brightly than older ones do. We need to be aware of these biases before we can use these observations to answer questions about what a normal solar system looks like.
We've already made a couple of references to the different compositions we expect of exoplanets of different sizes. Mostly, we've been assuming that exoplanet parameters would be similar to those of our solar system. When we look at theories of planet formation in an upcoming section, we'll go over some solid theoretical reasons for size and composition to be related. For example, since atmospheres are held on by gravity, a large planet is far more likely to hold a deep atmosphere than a small one. But the point of science is testing theories. So how do we test the composition of planets? Each of our detection methods gives us different information. Radial velocity gives the mass of the planet and the distance of its orbit. Transits and direct imaging both give the radius of the planet and the distance of its orbit. A few transit detections have given very rudimentary spectroscopy of the planet's atmosphere, and multi-wave band imaging gives temperature, but these are still in their early stages. If we know both mass and radius for a planet, then we can calculate its average density. And that puts us much closer to knowing its composition. This image, for instance, shows us how big 1 and 5 Earth-mass planets would be if they were made of a range of possible compositions. Real planets are likely to be of mixed composition, which will make it a little harder, but density will still give us a greatly improved idea of the possibilities. It's only possible to do this with the exoplanets for which we have multiple methods of detection, which is currently a minority of exoplanets, but there will be great effort to increase this number. In this Making Sense table, you should go through the 3 major ways that exoplanets are discovered and describe how they work, what information we can get from each, and what selection effects each has.